So maybe later we'll need to look at the case of a Calabi-Yau variety. So you want to think of this, well, of course, this could be like a constant family, and then there's not so much to say. So somehow, but you want to study whatever this means, xt as t tends to 0, right? So of course, this is just not so clear what is meant by that. But let me just give you one example of. So let's look at which will be in a Calabi-Yau. So let's say that xt is. So let me sit inside two-dimensional projective space. So let me do, so say x, y, z plus t, and then x cubed plus y cubed plus z cubed equal to 0 inside P2. Oops. So of course this, at least for t close to 0, this is it's an elliptic curve, or you can think of this as a geometrically, whatever that means, like a torus, but it's kind of a skinny torus, right? So because you see, if you plug in t equal to 0, something's going to happen. You can actually kind of change. I mean, essentially the torus as a Riemann surface has kind of two parameters here, and you can kind of see that it looks like this. So as t tends to 0, this xt should somehow converge to a circle, like a real one-dimensional manifold. And somehow part of the objective is to try to, well, not to prove necessarily, but at least to make these kind of statements precise. Right. So in what, I mean, I didn't say in what sense I want this convergence to happen, and that's exactly what I want to talk about. Okay. But just in order to be a little bit precise, I'm going to spend a lot of this first lecture not really talking about degeneration so much, but just kind of setting up formalism. So it'll be a little bit slow, and there'll be some overlap with a previous talk by Wojcicki. Okay. So I want to go back and just say what I mean by like algebraic projective varieties and complex manifolds, and so, I mean, not from the very beginning, but at least make some a little bit pedantic points, perhaps, right? So I'll get to a Calabi-Yau in a while as well, but whatever I'm going to work with are kind of, so I hope this is readable. So say smooth, complex, projective varieties, right? So what I mean, intrinsically, by this I just mean that x, I have some subvariety inside some Pn C. So this is just cut out by a bunch of homogeneous equations in n+1 complex variables. Okay, and then I assume it's this is just there's nothing particular about C, so at this level I can just define it over any field. So this is just algebraically, and then if you want this more intrinsically, so then maybe I want, well, you can do this in different ways. So maybe think of XL. So this is, say, a polarized variety. I mean, smooth, right? So X is some, well, a priori it will be projective as well, but a priori it's not, right? So this is some kind of algebraic variety over C. I mean, again, smooth, etc. And then I want L to be an ample line bundle. Okay. And then the sections, I mean, once I have this, then I get from I, this is just taking the global sections of L, embeds this into some projective, sorry, P. Maybe for N. Like this, or maybe a dual if you like. Okay. So that's slightly more intrinsic. And here, when I talk about line bundles, I will think of line bundles sometimes as kind of geometric objects as fibering like a total space, or as an invertible sheaf. Okay. So I haven't done very much. But you get some more. When you study this in its generality, somehow the main hero here is the canonical bundle. Right. So basically, so just sections. If I view this, so the sections of Kx are, well, holomorphic, or think of them as n-forms. Right? I mean, at this point, I haven't really defined what, there's no particular meaning of holomorphic n-forms. They're just kind of regular n-forms. Right? And where n is. Okay, and then of course you can go on. So there are kind of the three special cases which were already discussed in the last talk.